Hello and welcome to another daily coding problem. These are mostly tech interview questions. They don't really have anything to do with programming in the real world, but they're lots of fun. They're like puzzles. Most of these come from either the LeetCode.com top interview question list, or they come from dailycodingproblem.com, which is a email newsletter. Every day you get an email. It has a question in it and like an estimated difficulty, and then it also tells you the company that it came from. So today's question was asked by Facebook, and this question is actually on both the LeetCode list and it's on the daily coding question list as well. So I got this in my email yesterday, but I found it on LeetCode earlier as well. So it's a popular one. Given n non-negative integers representing an elevation map where the width of each bar is 1, compute how much water it is able to trap after raining, for example. And then we have an input and an output. Something I like here is they've given us a picture as well, so let's open that up. Let's make this a lot bigger. Okay, there we go. Whew. I can hardly see it, the pixels are so big now. Okay, so this is the example they've given us. We can look and confirm that. So we've got 0, 1, 0, 2, etc. And if we look here, 0, 1, 0, 2, 1, 0, 1, 1, 0, 1, etc. So what we're given is an array of heights, and these each represent a wall. And we need to return how much water is stored if it were to rain on top of our graph here. And I'm assuming the blue is water. That makes sense. So in this example, we would return 1, and then we have 2, 3, 4, 5, and 6, which is what we expect to get back. So I don't see any space and time requirements here, meaning we could, take forever and use insane amounts of space. But I know that typically with these kinds of questions, there's some trick involved that makes them pretty efficient. So we're gonna see if we can do it in linear time and a small amount of space. So that'll be either linear space or constant space. I think we can do this with constant space, the way I'm thinking about doing it right now, and linear time as well. So I'm thinking about a solution that would let us find this volume in, at most, 2 walks through our array. So that would be 2n, which is linear, and storing 1 value, which is the amount of water. So that would be constant space. So this is what I'm thinking. We can start at the beginning of our array and walk to the end. And as we do that, we'll keep track of the highest wall that we've seen. So we'll start here. The highest wall that we've seen is 0. We'll go to the next one. The highest wall we've seen now is 1. If this current square is shorter than the highest wall that we've seen, then we'll add the amount of water that we should collect. So for example, in 0, this is not shorter than the highest wall we've seen, so we add nothing. 1, this is not higher than the highest wall we've seen. Now we're on to the next square. Okay, this is a height of 0, which is less than 1, which is the highest wall we've seen so far, so we'll take 1 block and add it to our result. Now we go to our next one. We have 2. This is the tallest wall we've seen. It's not shorter than the tallest wall we've seen, so we're not going to be adding any water. Okay, now we have a 1, so we're going to add 1 block because it's 1 less than the tallest wall we've seen, etc. So we keep track of the tallest wall at each location. If that wall is shorter than the tallest wall, we'll add the difference between that wall and the tallest wall. We'll add that difference to our bucket of water. If the current wall is taller or equal to the tallest wall that we've seen, then we'll save that as the tallest wall and continue on. Now, once we get to the end here, this is where I'm thinking about doubling back. So as we fill with water, we're actually going to count these white squares here as water as well, right? Because we're gonna get here and it's gonna be a height of 2, and we're gonna take 3 minus 2 and we're gonna add a 1. But all this water at the end of the graph is gonna fall off. So what I'm thinking about doing is once we get to the end is starting at the end and going backwards all the way to the tallest wall and subtracting these bits of water that are gonna fall off the end of our graph, okay? So if this is complicated, let's start writing code and maybe it'll be a little bit more clear what I'm thinking. So they've given us a test. We'll definitely add more tests because this could be complicated, but we'll start with the one they've given us. Let's open up a solution and start writing out what we want this to look like. So we're gonna use Minitest auto run to run our tests, and we're gonna use Minitest pride so we get color in our output. And then we also want to include our solution, which is what we're gonna test. So now let's describe what that solution looks like. It's going to, you know what? I forgot to start my stopwatch. Okay, now it's started. Our time has started, even though I just wasted, I don't know how long, 10 minutes or something. Okay, so we have a solution. That solution is going to have a method. We can call that rainwater, I guess, right? It returns the amount of water between the walls. Returns the amount of rainwater between the walls. Okay, that's what our test looks like. Let's reopen our README, grab this example they've given us, and let's make a test for this. So we've got rainwater, and we expect to get back 6, right? Perfect. Let's go ahead and run this. Excellent, it fails as expected. We don't actually have a solution, so let's create that now. Class is solution, and let's add our method that we're testing as well, which is rainwater, and that takes some walls. Okay, let's give this a run now. Okay, we expected to get back 6 and we return 0 because we're doing nothing here. So let's do what we just talked about. We're gonna walk through our array, look at our walls, calculate the water, and then we're gonna walk backwards and subtract any water that's gonna fall off our graph because we're not, because we don't have a tall enough wall at the end, potentially. Maybe we do, maybe we don't. So we're gonna keep track of the water. So we'll have that as 0, and then we wanna return that at the end. So I'm gonna just stick it down there so we don't forget. Now we also talked about keeping track of the tallest, right? So let's do tallest, and we'll start that. This will actually be the index of the tallest wall. I think that'll be best, not the actual value, but the index. And is there anything else we need to keep track of? I think that's okay for now. We might have to add some more stuff in a second, but for right now, we have the water and the tallest. So now let's go through each of our walls, which will be the index of 0 up to walls.size -1. And this will be I. So now we have our current wall. If that current wall is taller, right? Let's do the other way. If the wall we're at is less than the tallest wall we've seen, then we know we're gonna be adding some water, right? So if our current wall is less than the tallest, then save that water. So we'll say water's tallest minus, we'll take the height of our tallest wall minus the height of the current wall. That's gonna be the amount of water. And then we'll go ahead and add that to our bucket of water, right? I think that makes sense. Now, if this isn't the case, if the wall that we're currently at is greater than or equal to our tallest wall, then we want to save that wall. So we're going to say tallest equals I. And is there anything else we need to do? We don't need to add water. We don't need to remove water, right? So I think that's good. So if we run this now, this is going to be wrong, but let's see. What would we expect? Let's get our picture back open again. And it's microscopic once again. Let's make it bigger. Whoa, too big. Okay. So right now we're adding up all the water, but we're still including water up here, right? Because we haven't subtracted this. So if we ran this now, we would expect to get back 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So we'd expect to get back 11, right? Let's see what happens. Okay, I have a typo. That's good, I guess. Walls, walls, here it is. Walls. Let's try it again. Okay, great. This is as expected. Our test did fail, but we got back the number we were looking for. So it's working. That's good, but we need to do step 2. So we got back 11. We expected 6. So now we can go the other way. We can start here, and we can walk all the way just to the tallest wall that we've seen and subtract these bits that are gonna fall off the end of the graph. So what does that look like? That is going to be the end of the array, which is size -1. And we're gonna go down to the tallest, but we don't need to include the tallest itself, so we can go +1, because we only need to go to this point here. We don't actually need to look at that wall. So walls.size -1 down to tallest +1. And this will be another I. And here's where we need to basically take our maximum height and subtract the height of the current wall, and then add any water that would be stored there, right? So it's going to be almost exactly the same as this. We're gonna go back through from end to beginning and add in the water, but also be subtracting the water that's gonna fall off, right? So what are we doing? We're gonna do, so first let's do our subtraction. So we have walls of, I guess we need to keep track of a second tallest wall too, don't we? We need to keep track of the tallest that we've seen on going this other direction. So let's call this other tallest. And we're gonna default this to the height of the element at the end of the array. So that's gonna be walls.size -1. And then we're going to take, here's where we subtract the water that's gonna fall off the end of the grid here. So it's gonna be walls of tallest minus walls of I. That's the water that's gonna fall off. So let's remove it from our bucket of water. And now we're going to add back to that the water that should be in this container. So for example, at this index right here, we're gonna take 3 and subtract 1, which is gonna take out these 2 pieces of water, and then we need to add back in that 1 piece that should be there. So if walls of I is less than walls of other tallest, then water, then we add to our bucket of water the amount of water that should be in there. Otherwise, other tallest is there. Otherwise, we save the other tallest and continue on. And then at the end, we return our water. Okay, I think we've done it. Let's try this. Excellent. That test worked. So let's add some other tests just to make sure there's not something fishy going on here. So I'm gonna draw a couple scenarios with hash marks here. So let's try one where the last wall is taller than the second wall. So all the water is not gonna drain off, but some of it will. So something like this. So this is a case where we have a last wall that will hold some water. So in this case, we would expect to hold just this drop of water that's in here, right? So that we're gonna expect to get back 1. And inside of our heights here is going to be 4, 2, and 3. Let's run that. Okay, great. That worked. Now let's try passing in something maybe like a downwards, like a ramp, a downwards ramp here. So I would expect this to hold no water, right? Because it would all just fall off the right-hand side. So this is going to be 0, and this is going to be 4, 3, 2. Okay, excellent, that works. Let's go the other way now. So we will take my goodness, drawing these things is brutal. Let me try. Can I do this? Okay. Okay, I'm done drawing now. Sorry, it's too much work. So now let's do a pyramid going the other way, or a ramp going the other way. So 1, 2, 3. So this would be kind of an ascending ramp. And again, I would expect this to hold 0. Okay, excellent. Now, what's another one we can do? So we've got one where the last wall is shorter than the first wall. We've got this one up here where the last wall is shorter than everything. Let's do one where the last wall is taller than the first wall, but we still have some water in there. So it's going to be similar to this one, actually. So it's going to be a 3, and let's just make this a 1 just for the sake of giggles here. I'm going to remove our picture because I'm not doing it for everything now, so it's kind of distracting. Okay, so this is the one we just edited, so our result is wrong. So let's see what it should be. So we have 3 and then a 1. So we would expect that to hold 1 piece of water. Oh, I guess it's still supposed to be 1, right? Let's run it. Oh, maybe not. Let's draw it. So 1, 2, 3. And then 1. Oh, yeah, it's 2, isn't it? I see it. I see it. It's gonna be real clear once we draw it here. Brutal. This is brutal. Drawing is brutal. Okay, so we got 3, 1, 4, and yeah, it does hold 2 because there's this piece and this piece. So that's great. I'm glad we drew it. Okay, so 2. Let's run this. Okay, excellent. So I think we're good to go. I think that's enough examples. I'm confident that our solution is working. Let's go ahead and save this and push it up to GitHub. So here is our solution. There's our tests. And we'll add a solution for today, which is the 3rd of March. And push it on up. Cool, that was a good one. My stopwatch says about 13 minutes, but I know we wasted probably another 10 minutes before that, so probably looking at around 20, 25 minutes for that. That's probably good enough in an interview. This isn't really an interview situation though. I'm very relaxed, I'm at home, I have a cup of coffee over here. But that was fun. Hopefully see you tomorrow. Thanks for joining me, bye.